Welcome back to this video where we will talk about the inverse of a function or a map. First of all, we have to start with a basic definition of the identity map or the identity function, which will be a function from the set to itself that taking x to itself. So here, let A be any non-empty set the identity of A as a function, usually we call it identity and we write A. It's taking as the input A and the output is again A. And for each x, I will assign x to itself. So basically this function do nothing, just take x to itself. And this is called the identity map or function. Of course, if we look at it, we will take the identity of any x, the answer will be just x. Keep this in your mind, and this is what we call it, the identity function. Sometimes we use a special notation for the identity. Sometimes we write it as identity of A. Some other book we will just write it as 1A. Some books will write it just IA, and so on. This is similar to the identity matrix because it has a kind of similarity. And now we will go to our main definition, which is the inverse. So what is the inverse and what we will do with the inverse is the following. So for the inverse, I will start with a function, a map from A to B, and an inverse map of f is a new function, it's a new map. We call it G from B into A. So now we opposite. The inverse is the output become input and the input become output. So if we do it in an arrow diagram, A, B, F will go from this direction and G will get me back in this direction. So it's the changing of the input and the output. Now what's the relation between them? Such that we have this relation. The first one, if we start with G composite with F, which means if you start here, you go with F, and then you come back, you should come back exactly where you have started, which means this is exactly the identity on A. Or we can write it in the different form as the following. We can write it as G of f of x is equal to x, which means it's kind of G and x, they kind of cancel each other. You can see that the only left is the input will survive as it is. So if we go with G and if we go with F and we come back with G, we will come back, we will end exactly where we have started. Same thing if we do the opposite. If we start with Y, if we start something here and we go with G, and then we come back, we end up exactly at Y. So this is the same as saying f of G of Y equal to Y. So this is exactly what the inverse means and how we define the inverse. So the inverse, it will just give me a way to move from one way to another, x, y. Go from x to y, come back to x, or go from y and come back to the same y. And as a notation, the inverse is denoted by, and usually we write it as f to the power of -1. of course, this doesn't mean it is 1 over f. This means this is g. This is a new function. It's a function by itself. Okay, so please just keep those things. We have learned the identity function and the inverse mapping here. Let's go and see some example. Example number 1, it says check whether the following function have an inverse or not. And let me start with the first one. The first one is easy to find the inverse, because if you have the cubic root and you want x to survive, definitely, sometimes we just can use g of y. Definitely, I would use the cubic root of y. Now, if you want, let's check what happened if we do g and f together. So this would be g of x cubed, and this means the cubic root of x cubed, and then x will survive. This is one way of checking the problem. Of course, we can check it from the other direction by starting with with f, and inside f we have g of y. And that's what I will do in the second equation, or second question here. So what is f inverse? If I have x plus 5 and I want x to survive, this means I take whatever there and let's subtract 5. Now let me check what happened if I start with f and then inside it f inverse. So check. This means f, and here we have y minus 5. Which means it will be y minus 5 plus 5, which is just y, which is exactly as expected. Now, for part C, and this is a very important question because it will give me how can I do the inverse function. Remember, the inverse function, I should go from A to somewhere, and then I should come back to itself. Remember, this is the inverse and this is the f. So in order to do that, of course, I have to assign A to some number 5. I have to assign B how many options left for me. Well, sometimes you would say it is 3 options. But let's see what happened if we assign B to 5. Now, if you do this, look what happened. If you start at A, you will go to 5. Now, how do you come back from 5? You have 2 options. Either you will land in A or you will land in B. We don't like this. The inverse should have only 1 arrow back. So, this cannot be the case. So actually, and in fact, I cannot have this dashed line. Let me just erase it. So I have only 2 options for B. So if you choose to go to 7, then the third option that this must go to 1. Now, if you look at this one, of course, the inverse is just changing the arrows. Now, if you look at this one, the first thing you can notice, it is 1 to 1. 1 input with 1 output, and 1 output with only 1 input. It's kind of a bijective. Can you see it's bijective? 1 to 1, and everything in the output goes to the input. Everything to the input goes to something in the output. We will come later to such an example. Now, look at this one. This one has no inverse. Well, why? Because remember, the inverse should be changing the arrow. So the 1 will go to C, that's fine. The 2 will go to A, that's super. The 4 will go to the B, that's perfect. But how about 3? It has nothing that it can go to. So this has no inverse. Which means everything in the output must be covered. So I can reverse the arrow, I can return them back. And that's exactly what I want to do. Look at this example, I think we just talked about it. Everything is fine, except where you will send 2 back. You have 2 options to the 2. So again, this has no inverse. So not every function has an inverse. We can see that we need it to be injective so that the arrows can go back exactly to one place. And I need it to be surjective so that everything has an arrow to go back to. And that's exactly my main theorem, which is theorem number 1, which says that a function has an inverse if and only if it is bijective. So having an inverse and bijective are exactly equivalent. Now, how do we going to prove such a statement? Well, as usual, because it is if and only if, B if and only if Q, we will prove that B implies Q first, and then we will do Q implies B. So let me do this direction first. So I will do it with direct proof. So we'll assume F has an inverse. I will call it for now G. And the required show F is bijective. Of course, if you remember how we show a function is bijective, it has two parts. First, I need to show the function is injective. And after I finish, I just need to show that the function is surjective. Remember, what is the relation between f and g? If we put them in each other, we get the input back. So let's do the injective first, and then I will do the surjective. How do I prove that a function is injective? I will assume f of x1 equal f of x2. What I will do next is a very clever idea. I will take g to both sides. So I will write g of this, g of this. Let's see what will happen if we do this. So I will write g, I will write g. Now remember, f and g, because they are inverse to each other, I will just get x1 to be survived, and here I will get x2 to be survived, so I get the function injective. So f is injective. On the other direction, let's prove that the function is surjective. Well. To prove a function is surjective, as usual, boom, boom, I have f here, and I have g here. How do we prove the function is surjective? There are steps to follow for surjectivity. The first one, we will say, let y be in B. So this is y, this is A. The next step, if you remember, this is step number 1. Next step, we write f of x equal to y. And now we need to isolate the x. We need to get the x alone in one side. So the only idea I have is to do the same as I did before. So to just put g to both sides, that will free for me the x. So I will get x equal g of y. Now, is this in A? Of course it is in A, because remember, g is from B to A. That's exactly how we define the inverse. It's just the opposite for this one. So we check, this is step number 3. So the function is surjective. So f is surjective. And if we put everything together, therefore f is bijective. It's a very nice proof, very good to practice this proof, and Please pause the video if you have any question of the first direction. I'll just leave it for you to look at it. We have to prove injective and surjective at the same time. Next, we will do the other direction, which we will assume that f is bijective, and we will try to prove that it has an inverse. So I need to find the g, I need to create the g. So the other direction, assume f is bijective, which means I know it is injective and I know it is surjective. Required for me, if I write it down, I will always remember it. Find an inverse G from B to A. How do we find an inverse G from B to A? Well, let me just do the arrow diagram. Sometimes it's helped me. I know F here. How about G? So you have to start with Y, and you need to try to find where Y will go. Well, okay, so let Y be an input. We need to find something in A that is related to Y. So I need to find how much G of Y, where G of Y will land. Let's see. Now, because Y is in B, by surjectivity of F, we know that there exists X in A such that f of x equal to y. This is the first thing I can get. So assign, and please pay attention here, I will declare that g of y is equal to x. So this is x actually. So I will declare this one. Now, let's see if we have problems with this or not. The first thing we need to check, there are many things to need to check, but let me just try to summarize them here. First of all, I need to check what happened if we have f and inside it g of y. Hopefully the answer is y. Also, I need to check what happened if we do this. Remember, I'm assuming I will get the inverse. So I have to check this, I have to check this. Hopefully, the answer here will be y and the answer here will be x. So they are inverse, they cancel each other. But before that, how do we know that we get only one x? The uniqueness of x. Remember, this arrow should go only to one place. It cannot go to two places, x dash. So, uniqueness of x. Now, let's assume there is another x dash in A such that f of x dash equal to y. Suppose we have another one, not just this x. Imagine we have another x. What do we get? In that case, what we know, f of x equal to y. Hence, f of x equal to f of x dash. So x equal to x dash. Why? F is injective. Okay, we finish. We assume that x, whatever we get, is unique. Now let's check f of g of y. F of g of y, it is actually f of x, and f of x is y. So this is good. Now, what is g f of x? I think this is just g of y, because f of x equal to y. And g of y is just x, so it has an inverse. I know this is the first time you see such an example, but it's very important to remember that the inverse is the same as saying the function is bijective. I'll just let you watch it for a second. Make sure you observe all the information here, and we will move on to the next one. Next, we have a very small corollary here saying that if inverse, the inverse is also bijective. The proof is very easy. Recall f has inverse. This is the same as saying f is bijective. Now, if we replace f inverse, we will get directly f inverse to be bijective. But f inverse has an inverse, which is f. So f inverse is bijective. The last theorem, which we already know, it is the composite theorem. If we go back from one place to another, how are we going to do this? And for that one, the answer will be very, very simple and easy. We can just do it in a second. Let's see the proof. What is the inverse of the composites? So GF inverse, and we take Z. Well, I don't know what is the answer, so let me call the answer W. Just for now, I will call it W. Now, the best idea is to do the same as we did before by adding G circle F and G circle F to both sides. Why? Because then I will cancel this one, I will get Z alone. Let's see what we get here. So okay, now of course this will be just Z, and this will be G of F of W. Now the first thing is take G to the other side. This will be G inverse of Z equal F of W. How do I take G inside? I just take G inverse to both sides. Get cancelled here, and that's what left. Do the same thing again. W will be just F inverse of G inverse of Z, which is the same as saying F inverse circle G inverse of Z. So the final answer here would be F inverse circle G inverse, which is, you can see the reverse between the two functions, and that's exactly what we are going to get. Thank you for watching. Please